We can use the valence electron trends on the periodic table in order to figure out how each of these elements is going to bond. So when we combine two or more elements together, or two or more atoms together, we end up forming compounds. That's what we're going to be investigating with this video. So here I have filled in the valence electron trends, and I've just put them over each of the main group element columns. Now we have what's called the octet rule. The octet rule states that each atom will gain, lose, or share electrons in order to form a perfect octet of electrons. So the octet is represented by the noble gas valence shell. That's where we have an S2P6. When you have only one valence electron, like in the alkali metals, or two valence electrons, like the alkaline earth metals, and we've seen the trends, how the ionization energy, the electron affinity, and the electronegativity go. If we have one or two valence electrons, they have a tendency to lose electrons. Metals tend to lose. Our nonmetals over here, our halogens, they will tend to gain electrons. When we lose electrons, all of a sudden we have more protons than electrons. So we form positive ions. That's more protons than electrons. And those positive ions are called cations. Now, in the first column grouper family, the alkali metals, they have one valence electron to lose. That means those elements are going to form 1+ common ions. So we would show them like this: hydrogen with a plus in the superscript, lithium with a plus, sodium a plus, and so on. The 1 is implied. We don't need to write a 1 there. In the second column grouper family, the alkaline earth metals, there are 2 valence electrons. And these electrons are likely to be lost. Remember the ionization energy, the electron affinity. We are more likely to form a cation over here. Our metals will lose electrons to form cations. So we show those cations with a 2 superscripted and then the charge, the plus. So that's just our convention, the number and then the charge, calcium, strontium, etc. Now our transition metals will also form cations. They tend to be a little bit trickier because we do have some special stability states. For example, if we start looking at some of our electron configurations in the transition metals, like here, we would have 3d4, 4s2. Now I'm specifically going to be talking about chromium in this instance. If we were to lose all 6 of these electrons, we would form chromium 6, or hexavalent chromium. We could also lose 3. That's these 2 and 1 of these. So chromium forms chrome 6 and chrome 3. Manganese forms a 2+. And iron has 3d6, 4s2. Now we can lose these 2 and form iron 2. But we can also lose one of the d electrons in order to form a special stability state with a half-filled orbital here. And that makes iron 3. Cobalt makes a +2. And nickel also makes a +2. Copper, however, now copper, we have 3d9, 4s2. Copper will lose those 2 s electrons, make a 2+, but it will also take one of these s electrons, put it into the d orbital in order to fill that d orbital, and then it only has one electron to give. So it will make a copper 1 and a copper 2. Silver just makes a +1. And gold, now gold is a little bit of an aberration. Gold is going to make a +1 and a +3. Zinc makes a +2. Cadmium makes a +2. And mercury here. Now mercury has a mercury 1 and a mercury 2. Mercury 1 is diatomic, so it's shown as Hg2, 2+, and we also have mercury, well, I put that in the wrong place, mercury 2, so mercury 2+. Now, as I'm saying this, I'm calling it, for example, chromium 6, chromium 3, and that indicates the charge on the cation. Now, as we move to the right, we get into our nonmetals. Now, as we move to the right also, we are increasing the electron affinity. The electron affinity, remember, was the energy change of adding an electron to a gaseous atom to form an anion. So as we increase that electron affinity, what we're doing is we're increasing the chance to gain an electron. If we gain an electron, we are making an anion. An anion is a negatively charged ion. So anion is what we're talking about here. So for example, fluorine, having an S2P5 valence shell, it can take on one more electron. When it takes on one more electron, it has one more electron than protons, so it has a negative charge. Chlorine as well. In fact, all of the elements here in the halogens will form a 1-. Moving next door, we have oxygen and sulfur specifically, and they have an S2P4. They have room to take on 2 electrons. So because they can take on 2 electrons, once they do that, they become S2P6. They have 2 more electrons than they have protons, so they become a 2- anion. And these are all called common ions. Everything I'm giving you is called the common ion. The transition metals, those that have more than one valence state. And when I say valence state, that's the charge on the ion. So if it has more than one valence state, it's a special case, and we're going to name those differently. Now, typically speaking, you're not going to see carbon as a ion. Typically speaking, you're going to see carbon share electrons rather than make an ion. Carbon has 4 valence electrons. It can either lose 4 or gain 4. Typically speaking, since it is a nonmetal, it's going to want to gain rather than lose. But carbon specifically wants to share, and we're going to go over the sharing as well. Now, as we make ions, as we make cations and we make anions, what we're doing is when we go to name them then, we're going to name them a little bit differently than we name the element. For example, if I have sodium as an ion, I'm just calling it sodium, but as soon as I put chlorine as an ion, I call that chloride. So when I go to make a compound out of these 2 ions, and that would be called an ionic compound, and I show that with a chemical formula. And to make a chemical formula, I take the chemical symbols of the elements. I note the charges when I'm looking at an ionic compound. I note those charges, and then I can make that compound. Now, because sodium is a +1 and chloride makes a -1, I would just name this sodium chloride, and the chemical formula is NaCl. The charges are equal and opposite. Now, whenever you write an ionic compound is made up of ions. Ions are metals and nonmetals. So whenever you write an ionic compound, the metal will always come first. Now, when you have a metal and a nonmetal, and they make an ionic compound, and their charges do not match, like this. we can still make a chemical compound. We just have to balance those charges. So because the sulfur is a 2- and the potassium is a 1+, that means I must have 2 potassiums to balance the charge of 1 sulfur. And this would be called potassium sulfide. So let's try a few more. Whenever we have a metal and a nonmetal, let's see, I'm going to pick N this time. Nitrogen will make a common ion. Nitrogen has the ability to take on 3 electrons, so it will be a 3-. Magnesium is going to be a 2+. It's going to give up 2 electrons. It's in column 2. So how are we going to balance these charges? Well, if I have a 2+ on magnesium and a 3- on nitrogen, we can use a technique called crossing our charges. So the numeral here will become the superscript here, and this superscript will become that subscript. So what I'm doing is effectively using the least common factor. So magnesium then takes on the numeric charge of nitrogen as its subscript. And then the nitrogen takes on the number associated with magnesium. So I've crossed the charges. That's what that technique is called. Again, whenever you have an ionic compound, and an ionic compound is made when a metal and a nonmetal react to form a compound, you always put the metal first. When we name it, we name the cation. So this would be magnesium. We take the root of the anion, and then we add "ide." So this would be magnesium nitride. Now again, these are called binary ionic compounds. Binary means there are only 2 elements. If we're going to name elements with, say, iron was one of our examples, that would make more than 1 charge. So we have iron 2 and we have iron 3. This is called a type 2 ionic compound. And if I'm going to make a compound with oxygen, and I'm going to use both of these irons. Oxygen's common ion is a 2-. Then I'm going to create a chemical formula, again putting the metal first, and this would be FeO because the charges are equal and opposite. And this one would be Fe2O3. So when we go to name these compounds, we need to identify which oxidation state we have, which charge we're using. So this one would be named iron, because that's the name of the cation, but now I need to use a Roman numeral to show what the charge of that iron is, because this is iron 2 oxide. This is iron 3 oxide. So you see, when written in narrative form, the only difference we have is that Roman numeral. But you can see the difference in the chemical formula very clearly, that we have either a 1-to-1 ratio iron to oxygen or a 2-to-3 iron to oxygen. So it's important that we designate which oxidation state we have for our cation when we can make more than one. When in doubt with a transition metal, go ahead and use the Roman numeral. Your first time doing it, I'm not going to be too particular about it unless you leave the Roman numeral off. So we have, let's do copper. Copper is another common one. Copper can make a +1 and it can make a +2. So if I combine copper with, say, chlorine, then I'm going to make my chemical formula. This time I need 2 chlorines to balance out the +2 charge of this copper. And this would be called copper 2 chloride. These two ions have equal and opposite charges. So their chemical formula would be CuCl. Now it is important to note that capitalization counts in chemistry. You need your capital C's and your lowercase second letters in this chemical formula. This is copper 1 chloride. So these are some examples of ionic compounds. Now these are, again, binary ionic compounds. We also have some polyatomic ions. Polyatomic ions is a group of atoms pushed together that as a unit make an ion. For example, OH with a negative charge. This is the formula for hydroxide. NO3, also with a negative charge, that's called nitrate. Now that's not to be confused with NO2 with a negative charge, which is called nitrite with an I. See, the difference is one letter. See, the difference is one oxygen. Here are some polyatomic ions, and it looks like I have a typo here. What I need to do, this is called phosphate. And I don't have the positive, the cation on here. There is one polyatomic cation that I tend to use in my classes, and this is called ammonium. So when we use a polyatomic ion, we're using it in its whole form. We're not going to break it up into anything else. So for example, if I have Na capital C capital N, then what I have used is the polyatomic anion. Well, no, that's too big. What I have used is cyanide, found right here. So I would name this by naming the cation, sodium, and then naming the anion, cyanide. You see the IDE, which we used for our singular atom anions, is already there. So if I was to do something like calcium phosphate and ask you to write the chemical formula, then I would expect that you would be able to know the standard or the common ion for calcium is 2+, and then phosphate from this list, phosphate is down here even though I had spelled it wrong when I typed it. So phosphate is PO4 3-. Now whenever you have a polyatomic ion and you need more than one, you need to use parentheses to indicate that you're going to be doubling, tripling, whatever of the polyatomic ion itself. So the least common factor here is 6. So we have a 2 and a 3. Or you can do your crossing charges. So I need 3 calciums in order to balance the charge on 2 phosphates. Notice how phosphate is in parentheses. If you only need 1, you don't use parentheses. But when you need more than 1, you do use parentheses. Of the common polyatomic ions that I like to use in my class, we have acetate. Acetate, when coupled with a hydrogen ion, becomes acetic acid. Cyanide you'll see, but just not that commonly. Chlorate. Perchlorate is part of bleach, so that's a good one to know. Hydrogen bicarbonate. Now, hydrogen bicarbonate is simply called bicarbonate most of the time. We have bisulfate or hydrogen sulfate here. Manganate. Permanganate is a fantastic oxidizing agent. Then we have nitrate and hydroxide. These are just the most common ones that you will see in my class. Peroxide, I should have more of it in, and carbonate is a good one as well. Now that's not to say you're not going to see the others. These are just the most common. If you're going to focus only on the most common things, then those are the ones you're going to want to focus on. They make up the largest percentage of my pool questions. So that would be what's called a polyatomic ionic compound, anything that uses one of these. Now, what we haven't talked about yet are the compounds that share electrons. We've talked about gaining and losing electrons. When we gain and lose electrons, we end up making ions. When we share electrons, we use what is called a covalent, or we make a covalent molecule. So co, meaning together, valent, like valence electrons. So we're sharing our valence electrons. Now we can only make covalent molecules out of non-metals. So an ionic compound has a metal and a non-metal, but a covalent molecule will only have 2 or more non-metals bound together. And when we name these compounds, because we're going to have a whole module based on shapes, so let's just focus on naming. When we name these molecules, then what we end up doing is naming the first compound. We'll use one that most people are familiar with. We'll start with this. We name the first element, carbon. And we're going to name the second element, but we have to pay attention to how many there are. And we're going to use a numerical prefix in order to indicate that. So this is carbon dioxide, di for 2. And that's different than this, which would be carbon, but we have to pay attention to how many of our second atom we have. We have 1, so we would use the numeric prefix mon. So this is carbon monoxide. Now, if we had something like P2O5, now we need to indicate that we have 2 Ps. So this would be diphosphorus, pent for 5, pentoxide. So you can see the numeric convention coming out. So we use mon for 1, di for 2, tri is 3, tetra for 4, pent for 5. Sometimes you'll see it penta. Depends on the letter that comes next. Hex for 6, and hept for 7, oct for 8, and it keeps going. Non for 9, and dec for 10. So we number and we name with our numbers. Now let's try a few more. Remember, naming with the molecule or covalent molecule formula. We are only naming compounds that are made up of non-metals. If we have a metal, then we have an ionic compound. So this, we would name our first atom, carbon. Because there's only one, we do not need a numerical signifier for the first atom. So this is carbon. Then we need a numerical signifier for our second atom, tetra, and then we name our second atom with the ide. So this is carbon, tetra, fluoride. And I seem to have dropped the O here, fluoride. If we have SBr2, we have sulfur, then we have dibromide. OF2 would be oxygen difluoride. So you see, with whether we gain, lose, or share, we should be able to identify both the chemical formula and the name of the compound. Now, if you are headed towards a medical or health sciences field, you may come across something like this. This is called silver nitrate. Remember, silver only forms the one cation, so we do not need a Roman numeral. Silver nitrate is a topical anti-infective agent. It's often used to treat and prevent eye infections. You may see this compound. This is barium sulfate. Barium sulfate is usually given as a contrast medium or an image enhancer in X-rays. You could see calcium sulfate as well. Calcium sulfate is used to make casts for broken bones. Potassium permanganate, it's a great oxidizing agent, and it's also a topical anti-infective. You may also find this in a survival kit because potassium permanganate can disinfect water. If it's pink, it's safe to drink. You could see lithium carbonate. Lithium carbonate is often used to treat bipolar or manic depressive disorders. And then there's magnesium hydroxide. Notice how this is a polyatomic ion. We use parentheses to indicate that we need two. Magnesium hydroxide is an antacid and a mild laxative. Then we have something like this. This is sodium fluoride. Sodium fluoride is used to strengthen teeth. It's probably in your toothpaste. And zinc oxide. Now, zinc oxide is used as a skin protectant. Now, this doesn't mean that you're not going to see covalent molecules in medicine. In fact, the majority of medicine is going to, where chemistry intersects with medicine, is largely organic chemistry. Organic chemistry is primarily covalently bonded molecules. If you have any questions, let me know.